continuing where we left off, we talked about solving for x, and in the next slide we'll look at this particular equation. Ignore this one. We're only looking at this equation, P1 V1 is equal to P2 V2. Now it says solve for P1. All right, if you were to use this equation, then you'd have to take T1 and T2 out, because you really don't even need T1 and T2. You're keeping the temperature constant. All right, this form P1 V1 is equal to P2 V2 is part of a gas law, the Boyle's law. Okay, so you're solving for P1. Okay, so 1 implies that this is an initial pressure, initial volume, and a final pressure and final volume. Okay, all right, so you're solving for P1, the initial pressure. What you can do is divide both sides by P1 or V1. Okay, so you can see that here they've divided both sides by V1, so you get rid of this V1, and so now P1 takes the form P2 V2 divided by V1. All right, so then you can plug in the corresponding numbers that corresponds with P2 V2 and V1, and then you can solve for P1. Okay, so the graph relationship has two variables. One is on the y-axis and the other is on the x-axis. Okay, so they're two perpendicular axes, and if those quantities, the two variables, have a direct relationship, then you will get a straight line graph, like we saw with in the graph that represented volume and temperature for the balloon. So volume of that balloon is plotted in liters on the x-axis, on the y-axis, sorry, and on the x-axis you had temperature in degrees centigrade. Okay, so the title of the graph will indicate what's happening, what is the relationship being studied, and that's the relationship being studied is volume of balloon versus temperature. Okay. So each data point on the plot was measured, the volume of the gas was measured at specific temperatures. Okay, so this straight line is indicating there is a direct relationship, both are increasing. All right, which is why the plot is a straight line. Okay, and then as I said before, you can then just because the major markings are at such high intervals, you can then break down, or rather not break down, you can then put in smaller markings in order to get an in-between temperature or an in-between volume. Okay. All right. Scientific notation. So if you have a number which is much greater than 1, like here, okay, or it's much less than 1, all right, then you can write it in what is called a scientific notation. And writing a number in scientific is that you have a coefficient followed by an exponent. All right, if the number is less than 1, the exponent is negative. All right, and the exponent is something raised to 10 to the power of 10. All right, if the number is a large number, then the exponent is positive. All right, the coefficient, the way you choose it is the coefficient has to be a number between 1 and 10. Okay. So for example, if you were going to convert 2400 into a scientific notation, then even though you don't have a visible decimal point, you imagine the decimal point to be here. All right, and then you're moving the decimal point 3 places to the left. Okay, so you moved it from here 1, 2, and 3, and this is a number greater than 1, therefore the exponent is positive. All right, so 2.4 times 10 power 3. right? So if you are converting a number much less than 1 into scientific, then you're moving the decimal point 1, 2, 3, and 4. And remember, the coefficient has to be a number between 1 and 10, all right? So you're moving the decimal point over here, 4 places to the right, and since the number is less than 1, that exponent is negative, all right? So the power is negative. So 8.6 times 10 power negative 4. Okay. So how do you interpret these powers of 10, and how can they be written in scientific notation? If the number is 1, it's just 0. The exponent here is 0, all right? So 1 times 10 power 0 is 1. If the number is 10, the decimal number, standard number is 10, then it's a power of 1, all right? So it's 1 times 10 to the power of 1, which is 10, all right? If the number is 100, then it's 10 times 10, so it's 1 times 10 raised to 2. There are 2 tens in that, all right? If it's 1,000, then it's 1 times 10 power 3, 10,000, 1 times 10 power 4. So 1/10 or 0.1 can be represented as 1 times 10 power negative 1, 1/100th as 1 times 10 power negative 2, 1,000th as 1 times 10 power negative 3, and 1/10,000 as 1 times 10 power negative 4. All right. So if you were going to write it in standard numbers, then you would have to write 0.01, 001, and so on. Okay. Okay, so when would scientific notation be useful? If you have a number like this, it's such a large number, right? Rather than writing out all of these zeros, it's so much easier to write it in scientific notation as 5.5 times 10 power 11, all right? Or if you have a number that's so much more less than 1, like here, all right? Again, it's way easier and it conserves time and space to write it in scientific as 1 times 10 power negative 19. All right. So when you have numbers greater than 1 or much less than 1, it makes sense to write it in scientific to save time and space. All right. You can also write the numbers that are not that big, like 68. You can write it in scientific as well. Okay. All right. So what is the key that you use to do scientific in your calculator? It has to be either the EE or EXP. Sometimes it's that caret symbol. Again, you'll have to figure out how it's done on your particular model of calculator. Okay. All right, so if you're doing 4 times 10 power 6, then it's 4 EE or EXP6, okay? And you'll see a display that looks something like this. If it's 2.10 power negative 4, then it's 2.5, or rather 2.5 times 10 power negative 4, then it's 2.5 EE EXP, and then plus minus. You'll use this function to convert that exponent into negative. Otherwise, it becomes a positive 4 if you don't do that, okay? So when you see a calculator display, then how do you interpret that? All right. So when you see a display like this, 7.52, and then there's a space and the 0.4, that means it's 10 to the power of 4, positive 4. All right. Sometimes it will be written like this, or sometimes there'll be the E and the 0.4. All right. If it is a negative exponent, then again you'll see a negative and then a 0.2, so that you have to write this down as 5.8 times 10 power negative 2. Okay. Again, get as familiar as you can with your model of calculator, and that would serve you well, and then you won't be struggling as to how to use your calculator during an exam especially. So writing the following in the correct scientific notation. So again, this is a number greater than 1. There's no visible decimal point. So you're going to move the decimal point, even though it's not visible, the decimal point is thought to be here. So you're going to move this 1, 2, 3, and 4 places to the left. So you'll be writing this as 6.4 times 10 power 4, positive 4. And then this, you will move the decimal point 1, 2 places to the right. So 2.1 times 10 power negative 2, because you moved it 2 places to the right, and this number is less than 1. All right, a bullet found at a crime scene has a mass of 15.24 grams. Okay. What are the place values for the digits in the mass of this bullet? Okay, 4 is in the hundredths place. This 2 is in the tenths place. 5 is in the ones place, and 1 is in the tenths place. Okay. All right, next one. The bullet found at a crime scene may be used as evidence in a trial if the percentage of the three metals, lead, lead, tin, and antimony, is a match for the composition of metals in a bullet from the suspect's ammunition. If a bullet found at the crime scene contains 13.9 grams of lead, 0.3 grams of tin, and 0.9 grams of antimony. All right, if you add all of these up, all right, 13.9 plus 0.3 plus 0.9, you should get 15.1. All right, okay. So let's see here what I can do. I can show you if I can get a hold of a calculator. Okay, and here it is. Can even bring it up. Okay, here it goes. All right, so 13.9 plus 0.3 plus 0.9, that should give you 15.1. all right, okay, so 13.9 divided by the 15.1 times 100. So the percentage of lead is, and it says express the answers to the ones place. So the ones place is over here. So 92% is lead. Okay. All right. 0.3 divided by the 15.1 times 100. Okay. So roughly 2% to the ones place, you're rounding it, it's greater than 5, so 2. All right, so 92% was lead, 2% is tin. Okay, that's total of 94%. And then you have 0.9 divided by 15.1 times 100. And again to the ones place, so this is 6. Okay, all right, so that does make sense because you have 92 for the lead, 2 for the tin, and then 6 for the antimony, so that's a total of 100%. all right, okay, so that's how you express your answers. Okay, all right, write each of the following in scientific notation. I'm sure you can do that. This will be 3.5 times 10 power 3. This would be 1.6 times 10 power negative 5. Okay, nurse administers Tylenol. The graph shows that the body temperature is decreasing, so body temperature on Y and the time on x-axis. Okay, and I'm sure you can answer those questions, and that will be the end of this video.